Hello, I'm Travis Gilbertson, and my capstone presentation is on termite evolution, how derived eusociality has influenced their life history, communication methods, and their symbiotic relationships. Here we have a phylogeny, and you can see Isotera, which is termites, and their closest living relative, which is Cryptocercidae, or wood roaches. And they're both members of the order Blattodea. So, termites, infraorder Isotera, order Blattodea, which contains cockroaches and termites. Like I said, the closest living relative is Cryptocercidae, wood roaches. And termites and both wood roaches share gut protists, so their common ancestor derived the same symbiotic relationship with gut protists. The first evidence of eusocial termites comes from Cretaceous amber, and there is a couple of indicators of a eusocial lifestyle. The first being differentiated castes. Now, castes are just different classes of termites: workers, soldiers, and reproductives. So, what they can see in these morphological differences is that the soldiers have snapping mandibles, the workers have smaller mandibles, and the reproductives are quite different. The queens are very large, the kings are also large, and the winged reproductives have wings unlike the other members of different castes. So, another amber showed signs of alloparental care, which means that the worker, there is just a worker or a couple of workers that take care of all of the larvae and nymphs in a colony, as compared to a solitary parental care in which parents would take care of the larvae. So, what shows us this is an aggregate of 89 individuals, which were soldiers and workers, and it had a lack of reproductives and larvae or nymphs. So what this shows us is that the larvae, nymphs, and the reproductives were all differentiated from this aggregate of workers and soldiers, which is a large indicator of alloparental care. There is a large amount of adaptive radiation, as I'll show you here in this phylogeny. So it was taken from amber samples. As you can see, the time period is the lower Cretaceous, is where that ancestor derives from. And the upper termites here, Neoisotera, were derived about 100 million years ago. So even the newer termites have been around for quite a long while. So my next point is going to be about how derived eusociality has influenced life history and survival patterns. So when an insect goes from being solitary to being eusocial or living in a colony, it's considered as a point of no return because they cannot survive without their colony anymore. Say a worker can't defend itself and it can't reproduce by itself. A soldier can't find its own food and it can't reproduce. And the reproductive class can't find its own food, and it can't defend itself. So these three different castes rely on each other to live. So there are some indicators of this that have been studied, such as workers who are in the presence of soldiers will exploit food resources faster than they would if the soldiers are not present. So they can tell that the soldiers are there to defend them in some capacity, so they feel more comfortable gathering these resources. Another indicator that has been studied is when non-colony mates are in the nest. Normally, soldiers are indifferent to them, don't care, but if there is a royal member of the colony near there, then the soldiers will be extremely aggressive towards the outsiders. So this is an evolutionary adaptation to ensure the survival of the reproductive individuals. The last one I'll talk about is how when there is no king or reproductive male present, the queen will go to individuals and they will molt into what is called a reproductive worker. So the queen is able to regulate the reproductive class of the colony in case something ever happens to the king. This is just a way of regulating. One thing I'd like to talk about in particular is juvenile hormone 3. So this is what is speculated to be the main source of caste differentiation, because when soldiers are molted, the titer of juvenile hormone 3 increases 4 to 5 times in their system, in their blood. A titer is just a measure of concentration in a liquid solute. So without this hormone, colony collapse would occur, and thus there have been studies looking at juvenile hormone 3 as a pest control method. Well, an analog of juvenile hormone 3, which would be inactive and the termites would not be able to use it. So colony collapse would happen in these situations. Here is just a diagram of what the different castes will look like. The soldiers, they have the mandibles. The workers have extremely smaller mandibles. Winged reproductives, which go off and make new colonies. The king, which is larger than the regular individuals. The queen, which is the largest, and the secondary queen, which is also larger than the regular individuals. So, throughout their evolutionary history, termites adapted derived communication techniques. So their pheromones are derived from cuticle hydrocarbons, and cuticle hydrocarbons are shared in all terrestrial insects or insecta. And what the cuticle is a part of the exoskeleton or chitin, which prevents desiccation through a lack of water, so it preserves water for these insects. So these cuticle hydrocarbons have derived a secondary purpose in all insects, so they can each create their individual pheromones. And termites have their own cuticle hydrocarbon pheromones, which they use for pathfinding, threat intruder detection, and caste identification. And there are predators and neutral symbionts of termites who use these termite CHC analogs to their advantage. So I mentioned alloparental care. So what this also includes is alloparental trophallaxis, which is feeding young individuals, larvae or nymphs. And this alloparental method of trophallaxis allows these termites to exchange cuticle hydrocarbons and communicate with each other very quickly. Here, I just wanted to show some relatives to insects along with the terrestrial insects. Insecta right here. So, a little over 450 million years ago. Another part of derived traits of termites is that they participate in obligate symbiosis. The most famous one being the gut protists in lower termites. Lower termites are ones that cannot digest wood on their own. And the alloparental trophallaxis I mentioned earlier allows termites to retain their endosymbionts that die every time they molt. So this is compared to solitary trophallaxis, in which they are not able to retain this endosymbiont. So some point in their evolutionary history, what are called higher termites lost their gut protists in some way. So there are a variety of methods that these termites use to digest wood. The first being the subfamily Macrotermitidae. They co-evolved with the mushroom Termitomyces. So this mushroom, they don't eat it, but it digests the wood for them, and they eat the digested wood. If you know about mushrooms, they digest externally and then they take in nutrients. The subfamilies Foramintermitidae and Sphaerotermitidae rely on spirochetes for the wood digestion. So they don't have protists, but they have this spiral bacteria which helps them digest wood. And this same family of bacteria is responsible for Lyme's disease and syphilis. I just thought that was an interesting tidbit to put in there. Here's just some derived traits of termites. Here we have the loss of protists, the three subfamilies I talked about. Didn't really cover this or this. And here we have the common ancestor of wood roaches and termites. So this is where they got the gut protists. Here's where they develop eusociality. And here's the wood roaches on the bottom here. Alright, so in conclusion, I have talked about how eusocial traits have allowed termites to specialize their roles in their colonies, which has affected their lifestyle and caused them to become more dependent on each other. This lifestyle has also derived communication methods like the cuticle hydrocarbons, and the eusociality has supported these obligate symbioses. The trophallaxis supports the gut protists, and it also supports the spirochete bacteria, and the colony life supports the growth of Termitomyces. Here's practical applications for humans. Like I mentioned, the juvenile hormone 3 could be used as a pest control method. And Termitomyces, something interesting about it is that it is edible, and it's actually considered a delicacy in Gao, India. So I would like to mention that it could be used as a sustainable food source, as there is little to no environmental impact on it. All right, thank you very much for listening. The next presentation